Okay, hello everybody. My name is Yu Yangdong from NEC Research Lab in Japan, and I will give introduce about our research named Deep Joinable Table Discovery with Pre-trained Language Models. And first, let me introduce about the background of the data lake. Data lake recently becomes a popular since that it just only save the data itself as a collection of data. And so data lake is a data repository that stores a lot of data. And it has the unstructured data or structured data, both of them. But in this work, and we focus on how to efficient discovery tabular data, which is the structured data, like the CSV tables from large table sets like the data lakes. So here. And another thing is that what is the table join? And join is a essential operation that it can connect the two more table together. So here is an example that here are two tables, and both of the table have the column of the race, and they have some same values in these columns. So for the two tables, if we just execute the EQ join between them, and we can join with the white and black records, and then we can get a large table after join them. So here is the join. And so this research is study about the joinable table discovery problem. It's given a query table and find joinable tables from data lakes. And the application of the joinable table discovery can be can be applied into the wild applications. So for example, we can do the table recommendations once we have the query table and we want to recommend the related table to our local table. Or on the other hand, we can just join the joinable tables find from the data lakes and to have more columns to enrich our local table. And so it can maybe improve the accuracy of the data analyzing task. And other things that we can do more data management. For example, the data lake is inside the company, and there have some heterogeneous data, and we want to manage them together. So if we can do the joinable table, we can just cluster the tables together. So here, yeah, the details of the problem definition is that given a query column Q, a big Q, and a collection of the columns big R, and output is that we find the top K columns with the highest joinability J. And the joinability between Q and X is defined as the matching records. So QM is the matching record, the number of the matching records between Q and M, and normalize the number as the size of the Q. So for example, and you know that the QM can be defined as based on the join types. For example, if we want to find the EQ join things, and the QM can be defined as to calculate the exactly match overlap between Q and X. And here is the example of the EQ join. So here is the query column, Tokyo, New York, Vancouver have three values, and we want to find top case. So for the first things is that the first column is Tokyo, Beijing, Vancouver, Toronto. And based on the definition, the joinability will be two over the three. Yes, they have two values exactly the same. The overlap is the two of the three. Yeah. And the motivation of this research is that we want to propose a general and efficient solutions. And first, the general means we need to support any kind of joinability. So for example, here are the related works for the different approach with the joinable table search. And we can find that the rule-based approach always only can support with only one kind of join type or one similarity between the records. So if we want to design a method or a framework to support all kinds of joinability, maybe the learning-based approach will be chose because we can adjust the different joinability with different training data. So for example, if we want to let the learn model to deal with the equal join. We just input them to the equal join label data. And if we want to let them support to the semantic join, we just to feed them with the semantic label data. Yes, so this is the one model for all. So deep join also have consider of this. So we want to focus on the learn-based. Actually, we use the pre-trained language model to fine-tune on it. Yeah. And another thing is that we want efficient solutions. For the efficient, we need to consider both accuracy and the speed. The first accuracy is that because we have the model, and the model will predict the joinability correctly. The model is trained the label and predict the joinability. We want them correctly. So the idea is that this is the work. The first thing, the first contribution of this work is that we are the first people who use the ability of the pre-trained language model on the joinable table research, joinable table discovery problem. So the first idea is that we use the pre-trained language model, and then this brings us a speed problem, because if we use, for example, if we use BERT to infer the joinability one by one, pairwise them. So if we predict pairwise columns, it will be computed. For example, if we have one query, we will compute n times. The n is the size of the data lake. It is too slow and too cost. It is impossible to do this. So here is a second idea, is that we use the embedding-based retrieval with the pre-trained language encoder. So we do not use pre-trained language model to predict. We use the embedding layer and to search, to embedding the columns into vectors, and then we can search these vectors. We can efficient search of the top K embedding vectors with the state-of-the-art approximate neighbor index. So this will change the complexity of this from NON to the O log n. This will be a very good performance. And then if we just if we want to embedding a columns into vectors, so we need a good embedding for the column joinability. So this second idea is that we just train the PML encoder with a metric learning styles. And these three ideas get together is the deep join itself. Okay, here is the overview of the deep join. Let's see the offline. Deep join actually is simple. And here is the data lakes. It has a lot of columns to index. We first transform the values of column to text. So there will be a lot of text. And then the text will be embedding to the vectors with a trained encoder. So after I will give introduce of the trained encoder. And then we embedding the index columns to the vectors, and we just index them into the AN index. For example, use the FICE library. And for online, when user upload his or her query column Q, and we use the same way to transform the column to the text, and then we get a text Q. We use the same train encoder to encode the query into a query vector, and then we just do the vector top K search to the AN index. So here is the overview. And first, let's see how we transform the columns to the text. The idea is that we not only use, so here is for example, here is the city of the Japanese cities. So it is Japanese cities, and there have some value of the cities. The idea is that we not only use these values, we also use the metadata, just like the column name and the table title, or if it's possible, we want to use some surrounding text between the tables. And we design a lot of patterns to include different metadata in them. So here is the patterns. For example, one of the pattern will transform the will transform the column into the city of the static. So here is a column name, here is a table name, contains 4 values, and the values, what is the values look like. So here is the text and for the input to the language model. And for the architecture of the deep drawing model, it's just a bi-encoder architecture. So we have 2 texts and we input them into the 2 encoder, actually 2 encoders. But in our setting, we just share the weights of this both 2 encoders. And then we got 2 vectors, and then we calculate the cosine similarity between the 2 vectors, and we use the loss function to let the cosine similarity as close as to the joinability of the training data. So this architecture named people always call the architecture like the bi-encoder or dual encoder, or if we share the weights, also code as the Sham's network. Okay. So the effect of the encoder is that the training encoder that here are 3 columns, and after embedding the columns into vectors, the similar columns will get closed into the latent space in the vector space, and the different column will be far away. Yeah. So we have then we can search of them. And the detail of the training is that we use the multiple negative ranking laws. It minimizes the approximate mean negative log probabilities. So the compute is in this formula. And the point is that it compute for one sample, it compute other negative sample together. So for the negative sample, we actually struggling at the negative sample. We try a lot of hard negatives, but we found that the in-batch random negatives in our experiment, in our setting, is the best solutions. So we just use the in-batch random negatives. And for data augmented, we also random shuffling the cells into the columns, so to create different kind of training data. Yes. And here is the experiment setting. We use 2 datasets, WDC web table dataset and the wiki table dataset. And we sample the both of the 2 datasets as the 1 million columns, so as the search target. And we also sample other 20,000 training positive pairs, like the EQ join pairs or the semantic join pair. The semantic join pairs is be calculated by the record similarity in the word embedding. So here is the compare method. We compare this method to the deep join, and deep join is implemented into the sentence BART, and the encoder we use the BART encoder and MPNet. The NN index we use the inverted file product quantization with the KNN graph HNSW. So for the time limit, we cannot show all of the data. So here is the representative data of the experiment is that. So here is the accuracy of the EQ joins. So into the 2 data sets, and the deep join is better than the compared method with up to 50% in the precision at K and 16% in the NDCG at K. And we also test the speeds. The speed is shown like this, and the results show that the embedding-based retrieval, which is the deep join method with the ANN index, is over 10 times faster than the traditional mean hash LRSH or the inverted index in Josie. And on the other hand, for the same vectors, for example, fast text vectors in the word embedding, and the deep join because deep join need to encode query online. And so this is the very cost part. And if we run deep join in the CPU environment, it will be slower than the fast text, maybe 4 or 5 times. But in the GPU environment, the deep join have the same level of the speed to the fast text. So that's all. This is my presentation. So if you have the questions.